Greetings and welcome to a new video about analog electronics. We continue with our non-inverting amplifier and this is our second example. In this circuit we will discuss a more complex circuit compared to example number 1. Of course we will look at our calculations step by step and also verify these in SPICE simulations. So let's look at our example. We have the following non-inverting amplifier circuit given here. We have a DC voltage source Vs and a couple of resistors R1, R2, R3 and R4 and also the load. And the values are shown here. And the load voltage is shown here in this case. And op-amp is again assumed to be an ideal op-amp. So what we will want to calculate is the following. Calculate the voltage gain expression. So V load over Vs, V source. And then also the value of the load voltage for the specific input and also the resistors. And we also like to know what the current is delivered by the op-amp IOP. Alright, let's look at our solutions. How do we start? Always we begin with the step 1 is determine the circuit conditions. Now for this op-amp, we know we have negative feedback. You can see that from here. So negative feedback. Around the op-amp, that means we have the V minus and the V plus. These two nodes will be equal to each other. That's actually the job or the result of the negative feedback. Since Vs is equal to V plus, we can say that is also equal to each other. That means also V minus is equal to Vs. Okay, now since ideal op-amp has the following characteristics, which is the infinite input impedance, we can say the currents entering the op-amp in this branch, in this terminal, I plus and also I minus are both 0, since we assume this is an open circuit for infinite input impedance. This is, by the way, a very handy characteristics for ideal case. Then we can analyze our circuit more easily. Now, let's look at our first question. Question A, the voltage gain. Load voltage over the source voltage. Now, before we move on, we need to first write the circuit equations. In this case, I again use node voltage analysis. I prefer that in most cases. So I will designate some nodes here. This is my node X, another one is node Y here, and I will also use this later node P. So I have 3 nodes in my circuit. By the way, node P is also the load node, so it is exactly the same. So if I also designate the polarities for each resistor and also the current direction, you can see the I1 is going in that direction, I2 here from right to left, I3 going from point P to point Y, and I4 going from point Y to ground. So this is just a choice. You can also have a different choice, doesn't matter. You will get exactly the same results. So now I will set up the loop equations or the current equations, actually, I must say, for each node. In this case, I will use the Kirchhoff's current law. So KCL at node X. That means the following. I2 will split in I1 and I minus. That's shown here, but we know from the ideal condition of the op-amp, I minus will be 0. So we can say I2 is just I1. The next step is using Ohm's law to write the current expressions here in terms of the voltages and the resistors. So we get for I2, because that's this voltage, is voltage drop between point Y and point X. That's actually shown here. So Y minus X over R2 will give you the current. In a similar form, we can do that for I1, that is Vx, this node voltage, minus the 0, that's of course still Vx, and over R1 will give you the current I1. That's actually shown here. Now, we know Vx is V minus, and V minus was V plus due to negative feedback, and V plus was Vs. So we can also replace the Vx by Vs. Now, we can still continue with our simplification of this expression, because we would like to have an expression for Vy, and that will be handy later. So because that is the final goal, again, remember, we need to have V load over V source. And if I have a different expression or another expression than the V load or Vs, something like Vi or Vx, I need to replace that. And I see in this expression that Vy and Vs is there. So I can say, let's then express Vy in terms of Vs, and then use it later in our expression where we can find the load voltage over the source voltage. So let's call this equation number 1 and then use it later. Now the Kirchhoff's current law again, but done in this case for node y. So KCL at node y. What we see is I3 will split in I2 and I4. That's actually shown here. Again, we will express each current expression using Ohm's law by voltage over resistors. So for this case, you see P minus Y. So Vp minus Y, but it's also V load. So V load minus Vy over R3. That's this part. For the R2, for this case, it is again Vy minus Vx over R2. And for this I4, that is just Vy minus 0, so Vy over R4. That's actually shown here. So everything is now written in voltages and resistors instead of currents. The reason for this again is that we know more here than in this expression. So that is the reason for, let's say, make it in more detail. Okay, now we again know that Vx is Vs, so we can just replace that as the only change actually from going here to there. And now we have an expression where you again see Vy, also V load, and also V source, and also some resistors. But this is not the final form we want. We only want an expression, the load voltage, the source voltage, so VL and Vs, and some resistors. That's actually what you really need to have. And the rest of the parameters you need to substitute or replace that. So Vy need to be replaced. That's also the reason why we have another expression here, the first expression. So if I now multiply the left and the right hand side of this equation by R2 times R3 times R4, I get this for the left side. So you can see, so the R3 will drop. And again, same thing here, but then I will lose R2. That's actually shown here. And again, the same thing for this final term. And R4 will drop, so you will get this. So what I have done is, again, repeat, the multiplication of the left hand side and the right hand side by the product of three resistors, R2, R3, and R4. So you will get this one. Now, if you work out the parentheses here and also replace the components with each other, you will get this. So I have now R2 times R4 times VL, which is on the left side of this equation. I also have the same coefficient for Vy, which is a minus sign, but it goes to the right hand side. And I have now an expression for Vy collecting this term, and also the term from the left side. And I also see a Vs alone, so minus R3 times R4 and Vs. And that's actually the expression here. Now we can see easily what's happening here because this expression has only Vy that need to be replaced. So we can also say let's divide then out the left and right hand side by R2 times R4. So that's actually done here. This is 1, because if you divide R2 over R4, you will get 1. This will be then R3 over R2, and this will be then R3 over R4. And also divide this by this expression, so you will get R3 over R2. So this is now the sort of the expression we can now name as equation number 2 and use it with this equation number 1 to move towards the expression for the voltage gain. So let's collect them here. Equation number 1 and equation number 2. Okay, let's now substitute equation number 1 in here in equation number 2 in this place. So what we get is the following. Now you can see directly what we wanted from the beginning. This is an expression having only V load, only Vs, and some resistors. Of course, it's not in a nice form, but it's already the, let's say, the frame we want to have. Now the next steps are just simplification to have a nice expression. So we can now do the following. That is one of the options. You can say, okay, I will now work out the parentheses. So 1 times 1, 1 times R2 over R1, and then also for this term, so you get actually 6 terms. So let's do that. So you see 1, 2, 3, 4, 5, 6 terms, and also this term is always there. So you get this. Now, if I look at it, I have this and also this, but I see here minus R3 over R2, which is also shown here. So I can say delete this or cancel these parts because it's also multiplied by Vs. Then I also see the R2 and R2 that can be divided out, and you will have these things. So by these two changes, you will lose this R3 over R2 and also will be R3 over R1 here. So we have now an expression, still not very nice, but much better than the first case. And we have now an expression of V load as a function of the resistors and the source voltage. Now what we can do, we can see the R1 and R1 here in the denominator for each term, so we can bring them together. That is one step we can do. We can also bring these two fractions together if I multiply this, so the fourth term, by R1 in the numerator and also the denominator, so you have then a common denominator. So the next step is that. So we will bring these two, so R2 over R1 and also R3 over R1 together, because they have the same denominator. And this is also taken together by multiplying first R3 by R1. Then we have the same denominator also here. Now we have this expression. Now what you can do also here, continue, is you can take out the R3 out this numerator. So you can take this and also do R3 over R4 and then get here R1 plus R2 over R1. So the rest stays the same. Now why is this handy? Now we have an R1 plus R2 over R1, which is 1 plus R2 over R1. That's shown here. And this expression here, this part, only this part, is what we know from the simple non-inverting amplifier. The basic circuit has only the feedback resistor R2, so no R3 or R4, and also this resistor going from this inverting input to ground. And the voltage gain was there, 1 plus R2 over R1. So this part is from there. And the rest is due to that extra two resistors we have here, so R3 and R4. So we can get more gain or less gain, depending on, of course, the choice of the resistors from this circuit. So it has more flexibility, more freedom. Okay, now we have our expression for the gain. Now, this is then the expression for the voltage gain, so we can now divide by the source, so VL over Vs is the thing in the parentheses. So that's actually what you see here. Now, if I now substitute everything here, just the values of the resistors, so R1 up to R4, you will have 26 plus 26 as the gain. If you, for example, only use R2 and R1, so don't have these R3 and R4 here, the gain was then 1 plus R2 over R1. Now 1 plus R2 and R1 is giving these values is just 10. So you go up by, let's say, from 10 to 26 by only using these two resistor values. So no additional, let's say, op-amp required in this case. Okay, that's for equation or question number A. We also need this equation later, so I will just place it here. Now going to the load voltage, this is very actually easy because we know the expression for load over source voltage, which is 26. I also need the load voltage by having the Vs of 2 volts, so we can express this in this form. Just substitute the values, we will get 52 volts for our load voltage VL. Okay. The current delivered by the op-amp, IOP, is again determined using Kirchhoff's current law at node P, because IOP will split in I3 and IL. That's shown here. So we can again say, let's express the currents here in terms of the voltage and the resistor using Ohm's law. So V for the I3, which is then VP or VUL minus VY over R3, and for the I load, for this load current, is VL over R load, which is shown here. So the load resistor actually comes in play when you talk about the current delivered by the op-amp, not in the voltage gain expressions. So we have now this. Now we of course need that Vy. We don't know that, but we have an expression. That's also why we have it here. So we can say, if I now use this expression and just substitute the values, and this will give me 10 volts. So we know this is 10 volts. This is already calculated in question B, that is 52. So we can now substitute everything, also the R3 and R load. We have this. If you now do the math here, you will get 174 milliamps. That's the current delivered by the op-amp. So we have now everything. So let's collect them together here, A, B, C, and these are the results for this exercise. Now, of course, we need to simulate this. We will like to verify these calculations. Now this is a circuit I've prepared in the SPICE simulator. You can see the voltage source of 2 volts, the resistors, and also the current arrow to measure the current in this branch, and also the voltage node pin here to measure the voltage at this node with respect to ground. So we see here 174 milliamps as calculated and 52 volts as calculated when the Vs is 2 volts and also the resistors as shown. You can get more information if you do, for example, a table of results. This is again the circuit, but then now the nodes designated clearly, 1, 3, 5, etc. You can see here the following. One important thing, very interesting. This 3 here is 2 volts. It's saying here VP_2 is 2 volts. Why? Because that's due to negative feedback. We said this node, which is shown here actually, V plus and V minus, must be equal to each other. Now, since this is 2 volts, this is also V plus, and this is V minus, then that means this node voltage must be 2 volts. That's also the reason why you have here 2 volts. This is again a proof that this is indeed the 2 volts due to negative feedback. You also see the V load here, again 52 volts, and also the IOP 174. So again, proving that this is correct. So everything is now verified also in the simulator. Now let's also jump now to the actual simulator and see how we can generate this table and also how we can make up these values in the simulator. So let's now jump to the SPICE simulator. Alright, we are now in the SPICE simulator. You can see the circuit, ideal op-amp, Vs of 2 volts, and the resistors R1, R2, R3, R4, and also the load. This current arrow will measure here the current in this branch, and this voltage pin will measure the voltage at this node with respect to ground. You can get this arrow from meters, that's shown here. So this is the current arrow, you click on it, and you can also give it a different name by clicking on that one. And you can also get this voltage pin from here. This is the voltage pin, click on it, and you can place it anywhere you want, for example here or there, to get that specific voltage at this node with respect to ground. Okay, now let's now do this circuit. I already prepared that, and then do DC analysis. So you go first to analysis, DC analysis, and calculate node voltages. That means you get all the information in your circuit where you want to measure the current or voltages. That's exactly what we want. So 174 and milliamps and 52 volts. You can also look at specific, let's say, resistor. So if I click on load, it will be highlighted in red. You can see the specific voltage, which is 52 of course, and also the current, which is 104 milliamps, specifically for the load. If I do this, it will be 42 and 70 milliamps, 42 volts, 70 milliamps. This is of course nice to see that this is 104 milliamps, this is 70 milliamps, together again 174. So that proves again the Kirchhoff's current law at this node here. You can also highlight this, for example, or this, or that, it doesn't matter. So you can see what kind of voltage and currents you have in a specific element. You can also highlight this node, which is now 2 volts. So you can again prove that this is due to negative feedback, exact same as the source of this node voltage. In addition, you can do, in order to get more information, do analysis again, DC analysis, because we have DC circuit, and you go to the table of DC result. Now you get a table here, generate a lot of information, so we will now unfold this. Now what you have is a couple of information here, but in order to get the right information directly, you can click on any component, let's say this one, or the node, and it will be highlighted in red. You can see it is 52. Or the component itself, then you get and the current and also the voltage together. You can also get here what the IOP is, that's actually shown here, the top one, 174. So everything actually is shown here, VL also, and also the VP_3, which is 2 volts as discussed in the previous discussion using the simulation results. Alright guys, this is for our second example about the non-inverting amplifier using some more complex circuit than the previous example, example number 1. Of course, we will move on with other examples to illustrate the concept of op-amp circuits, so stay tuned. If you have any questions, comments about this or any other exercise in this play series or the videos on my channel, just let me know and I will try to answer for them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.